Hello all, in this lesson we're going to be doing our first lesson in Unit 12, Organic Chemistry, and we're just going to go over the basics in this lesson, including what makes carbon so special. The homework associated with this lesson is here. We'll do that in class, and the aim you need to copy down now is how do carbon atoms bond. And let's draw this molecule together and we'll make observations of it tomorrow. So let's start with this ring, which is all carbon, and I'll add some attachments now. So there was a carbon attachment up here that had a double bonded oxygen, and we have a single bonded oxygen with one hydrogen coming off. Over on the right hand side we have an oxygen bridge and another carbon with a double bonded oxygen, and it's also heading up here to another carbon that has three hydrogens. And this dotted line right here on the center of the molecule is actually an alternating double bond. In other words, you have a double bond here, single bond right here, but we're going to have a double bond again here, single bond here, and a double bond there. So that is the structure. What you guys need to do is just copy this down, and then we'll make observations in class tomorrow. Okay, organic chemistry. To most people, organic just means like healthy, pesticide-free. But organic actually has a different definition, which you may remember from Living Environment, and that definition is a molecule that contains both carbon and hydrogen. But I think in this one case, the scientists who studied organic chemistry and first gave it its name had their hearts in the right place, because they thought that organic chemistry was the chemistry of life, or the chemistry of living things. And basically they just thought that the molecules that we considered organic could only be made by living things and could not be synthesized in a lab. And of course, this is not true. We did a lot of experiments to figure this out, but the first person who was able to synthesize an organic compound, meaning a compound that contains carbon and hydrogen, in a lab was a German scientist depicted here, and his name was Friedrich Wöhler. And he used an ammonium ion combining with a cyanate ion, and he was able to fuse them together to make urea. Urea is the compound in our urine that gives it its smell. It's not a very glamorous first organic molecule to make, but it was easier than most, and it did show that it could be done. And from there, we've opened up organic chemistry to this wide, wide world of molecules that really starts with the electron structure of carbon. So one thing I want you guys to notice right now is that carbon has 4 electrons in its valence shell. There's one down here, there's one there. And so does silicon, actually, which makes sense considering that silicon is in the same group as carbon. And that means that silicon can make all of the same bonds that carbon can make. And that is the reason why some scientists, although not the regents, consider molecules containing carbon or silicon and hydrogen to be organic. Alright, so let's talk more about the electron arrangement of carbon. First of all, carbon's electron arrangement is what gives it all of its special abilities, so I will highlight that item for you now. And carbon has 4 electrons in its valence shell, which is the reason why it is equally likely to gain or lose 4 electrons. Although technically it is slightly more likely that it would gain 4 electrons because the octet is more stable than the duet. So this also tells us how many bonds a carbon atom can make. If it needs to gain 4 electrons, then that means it can share 4 electrons for 4 separate bonds. And since all atoms are three-dimensional, meaning not flat like this diagram of carbon would suggest, then that means that all of these electrons are going to spread out in 3D space as much as they can. Now in 2D space, the most they can spread out is 90 degrees. But in 2D space, they can spread out to a whopping 109.5 degrees. So that's why the atoms of carbon with their 4 electrons in their valence shell actually will point their electrons toward the corners of a tetrahedron. This is a tetrahedron. It's just a polygon that has 4 sides. So here's one of the sides in the back, and here's a side on the side, and here's a side in the front, and there's a side on the bottom as well. So there's your 4-sided pyramid, but you can see it here as well. There's going to be a side between these 3 hydrogens. There'll be a side in the back with those 3 hydrogens, and there will be a side in the front with these 3 hydrogens, and then on the bottom there's a side with those 3 hydrogens. In the lesson tomorrow I'll be able to show you this animation. But yes, tetrahedron. Let's highlight that because that is very important. Okay, when carbon atoms bond, they share their electrons because they tend to be covalent. And covalently bonded molecules will tend to have the properties of covalent molecules. And those molecules are that the bond and the molecule shape are generally both considered nonpolar. Now, there are some cases when you'll see some polarity, like for instance in this molecule, it's covalent, but you can see that it's not exactly symmetrical, but still more symmetrical than it is not. Again, these bonds may not all be completely nonpolar, like this bond between the C and the H would be considered a polar bond. However, it's much more covalent than it would be, let's say, if it were a metal and a nonmetal. So in general, we consider these guys nonpolar bonds and nonpolar molecules as well. Now, for the melting and boiling point, we'll also just borrow that from molecules. Molecules have low melting and low boiling points, so let's give the same properties to organic molecules. Furthermore, if these guys are nonpolar, then they're going to be soluble in nonpolar solvents. And the only thing on this list that's sort of new and maybe interesting to you is that the reaction rate of a covalent molecule will always be pretty slow. And the reason for that is because a reaction requires that some bonds break and other bonds form. So when we're trying to break one of these bonds, these covalent bonds are pretty strong, so their reaction rates will be pretty slow. And we also know that carbon atoms can make, of course, 4 covalent bonds with all of these properties to their neighbors, and we can check to see if a molecule is drawn correctly by counting those 4 bonds. So all of these molecules have carbons that have 4 bonds each. Some of that is pretty obvious. I'll highlight those areas in red. Like this carbon, it's pretty obvious that it has 4 bonds. This carbon, sure. Here and here, yes, they all have 4 bonds. And this carbon is pretty obvious as well, but the others maybe we should be more specific about. So this carbon, it does have 1 bond right here, and it has 2 and 3 right here. That's a double bond, so there's 1, 2, 3, and here's the 4th. So that carbon has 4 bonds, and similarly, this carbon has 1, 2, 3, 4 bonds as well. So it's going to join the club of 4 bonds. And then we need to go over to these 2 carbons. And this carbon has 1 bond there, and it has 2, 3, and 4 right there. So it also joins the club of 4 bonds. And the last carbon has 1, 2, 3, and 4 right there. So all of these carbon atoms, they all had 4 bonds each, and that's something that they do have in common. And if you're counting their carbons, they all have, let's see, 3 carbons as well. So I have to ask the question, do the molecules below have differences, or do they only have things that they have in common? So if you're looking at these pretty closely, you will see differences between these molecules. For instance, this carbon-carbon bond is a double bond, and this carbon-carbon bond is a triple bond. This one has neither double nor triple. And this one seems to have the most hydrogens and the most single bonds. In fact, it only has single bonds. And this is what I mean by saturated. So the molecule that is saturated is, of course, this one. And with what is it saturated? We could say single bonds, and maybe some people would say hydrogens. But I'm going to say single bonds because I know that's what the Regents would say. So you guys know several different kinds of formulas. There are ionic formulas, for instance. We have molecular formulas. We have empirical formulas. And one of the ones that I'm going to teach you on this slide is the structural formula. A structural formula will still use letters to represent elements, like C's and H's, but it employs the two-dimensional space of the paper to show you some of the structure of the molecule. It cannot show all the structure because molecules are three-dimensional. So structural formulas give you certain kinds of information. Quantitatively, it gives you the number of atoms of each type of element, but qualitatively, it tells you the type of bonding and some of the shape of a molecule. So one of the things we're going to do in class is we're going to use a molecular modeling set, or a MoLeMod, to make a structural formula for the molecule on the far left. This guy, his name is methane. And it's a really powerful greenhouse gas. It's also just a component of natural gas, and has a very distinctive smell. But we'll model that with MoLeMods in class. And that brings us to the pair up. So guys, please copy down these pair up questions. We'll do them in class tomorrow. And follow them up with this summary, which we'll do in class tomorrow as well. I know this guy looks pretty weird, but I think you know to read it: CH3, CH2, CH3. I hope you learned something, and thanks for watching.